All right, everyone, we're very pleased to have Ben Bakker visiting all the way from virtually at UIC, I guess. Yeah, welcome, Ben. Take it away.
Right, thanks. Thanks so much. It's a pleasure to be back, such as it is. Yeah, to explain a little bit about some O-minimal stuff. Um, I meant this to be, a little informal, A, because it's expository, and B, because my iPad died recently, so I threw together these slides yesterday, so I apologize in advance if there are some issues. But anyway, my point is that it's informal, so yeah, you should just interrupt me whenever you want to ask questions. Okay, so my understanding is sort of you're looking at them like the intersections, and maybe going to be talking about Pila-Wilkie soon. So there's many ways to sort of motivate O-minimality, which sounds a lot more complicated than it is, as we'll see. It's a very simple definition, but I want to sort of motivate it via what will eventually be the Pila-Wilkie theorem. And I'm going to do that by first talking about a precursor to Pila-Wilkie, which is the Pila-Bombieri theorem. And the statement is very simple. It's the following. If we have a compact real analytic curve inside the real plane, which is not algebraic, then if I sort of start scaling this curve up and up and up, then there's a bound on sort of how many integral points this curve can pick up. Okay, and sort of you can see immediately that this is not true for an algebraic curve, because you could take, for instance, the circle and start scaling it up, and then we'll have many points. So you should view this as sort of a way of distinguishing between sort of algebraic and analytic things, curves, in terms of the sort of number of rational points or the integral points in this case, in a way that I'll make more precise later on. But sort of the slogan here is that when you start scaling this curve up, if it's not algebraic, then it has sort of fewer than polynomially many points, integral points.
Sorry, I have a stupid question maybe. What
Sure.
if the curve was like 2 to the x? Y equals 2 to the x.
Yeah, what if it's 2 to the x?
Then aren't there infinitely many intersection points?
Well, I mean, how is the graph of 2 to the x a compact real analytic curve?
Oh, compact. I missed that.
Yes.
Excellent.
No. That's going to be an important point.
Cool.
Compactness is essential.
Cool.
So let me just give sort of a very quick idea for sort of how this works. There's sort of two steps to the argument here. Oops. The first part is sort of a bound on how do I want to phrase it? It's sort of a bound on the sort of complicatedness of the integral points on a curve based only on sort of its derivatives. Okay, so let me explain that a little bit. So more precisely, given a real analytic function on an interval of a certain length n, there's a bound purely in terms of how to say it. So the correct statement is you can put all the integer points realized by the graph of this real analytic function can be fit onto a number of degree d algebraic curves, which depends in a very precise way on the length of the interval and the degree of the curve. Okay, and the sort of order of the derivatives. And sort of the way you should think about this is if you sort of control the normalized size of the derivatives of this function on this interval, then it can only be so wiggly. So it sort of can't go through too many integer points that are too close together. And therefore I can sort of quantify sort of how many algebraic curves I need in order to go through all those integer points. And then the crucial part is I can also understand how this depends on degree. Sort of in some sense, like if you allow yourself to use bigger degree curves, then you can get algebraic curves that sort of go through the integer points more efficiently. And so it takes fewer algebraic curves to fill out all the integer points of the graph of f. Okay, So this kind of lemma is sort of the key part of the theorem, but it sort of uses very sort of classical arguments in analytic geometry and sort of understanding sort of how, efficiently you can go through integer points with having controlled derivatives. Okay, any questions about that? Okay, and then the second statement comes from sort of a compactness statement. The point is the space of degree d curves is compact. So there's given a d, there's a bound on the total number of intersections of degree d curves with all possible scalings of the graph of this function f. Okay, so now to sort of get to prove the theorem, basically given an epsilon, you choose a degree d so that the exponent that appears here is small enough. It gets smaller and smaller with d. And then the constant that you'll get here depends on the sort of maximum size of an intersection of a degree d curve with f, because we know that we can fit all the integer points on this sort of fixed number of degree d curves, which has this precise behavior when I start scaling my interval. Okay, so that's the idea. Again, I don't want to spend too much time on this because this is probably talk about it more later, and this is more for motivation. But this is the idea. And as Daniel already pointed out, there's lots of ways in which this is false if C is not compact. The easiest way to make it false is if your curve just goes off to infinity. So, in particular, it might just not have finitely many integer points. If it has infinitely many integer points, then you sort of have a problem even formulating the statement. So the function I chose was the graph of sine 2 pi x, but 2 to the x is also a problem. Although, well, no, yeah, that's also a problem. Okay, so we need some sort of tameness properties of C, whether that be some boundedness statement, or we need some statement about sort of what's going on as this curve goes to infinity, okay? And at its heart, O-minimality is a sort of very precise tameness property of subsets of Rn, which is sort of very easy to work with because they satisfy sort of a nice sort of inductive structure that'll be very familiar to anyone who's coming from algebraic geometry. Okay, so let's dive into the definition. Okay, let's start with what's known as a structure, which is terrible terminology, but that's how it goes by. So let me first define what a structure is. So a structure S is a collection Sn indexed by the natural numbers, where each Sn specifies a certain set of subsets of Rn. Okay, so the way you should think about it is S sub n is telling you what the tame subsets of Rn that are allowed in this theory are going to be, right? So this, the structure is supposed to give us a language in which to talk about tameness, and this Sn is telling you what the tame subsets of Rn are with respect to the structure. And we want this tameness property to satisfy some axioms. Okay, so the first of which is, in a fixed Rn, if I take any two tame subsets, then their intersection and union is also tame. So it's also in this collection Sn. And the complement of anything in Sn is in Sn. Moreover, I want all of the Sns taken together to be closed under both Cartesian product and coordinate projection. Meaning if I take sort of a subset of Rn that's in Sn and a subset of Rm that's in Sm, and I take their Cartesian product, that's a subset of Rn plus m, and it should be inside Sn plus m. Okay, and likewise with coordinate projection. And finally, I want to sort of seed my structure with something. So I sort of throw in all real algebraic sets. Okay, so for any real polynomial p in variables x1 through xn, if you look at a zero set, p equals 0, that's a subset of Rn, and I declare that to be tame. Okay, I declare that to be inside Sn. Okay, so I've been using the word tame because that's ultimately what we're trying to capture, but there's a precise word we use for the subsets of Rn picked out by this structure. We say that a subset of Rn, which is in Sn, is said to be, is definable within the structure, or is S definable. And likewise, if we have a definable subset of Rn and a definable subset of Rm, and we have a function between them, then we say the function is definable within the structure if its graph is as a subset of R to the n plus n. Okay, so let me just pause here, just so everyone can fully absorb the axioms. These are like, let me just stress, it's super simple axioms. This is like as complicated as sort of the O-minimality as we're going to address it is going to become.
When you say coordinate projection, that means all of this is dependent on fixing some basis, or?
That's an excellent point. So ultimately, yes, the statement in the second point does depend on choosing a basis. But note, so I mean, it's an easy exercise to show that the composition of definable functions is definable, and the image of a definable set under a definable function is definable. So because of the third point here, I'm allowing myself, in particular, all linear functions. They're all definable. And so the change of coordinates are all definable. So in fact, any linear projection is definable. Yeah, any other questions? Cool, okay, so there's some very easy first examples. Actually, the easiest first example is a non-example. So let's just take the sets that we have. Let S be the collection of all real algebraic sets, meaning take each Sn to be the Boolean algebra generated by the real algebraic subsets. Okay, now this is not a structure. And the problem is that it doesn't satisfy the projection axiom, because if I take any real polynomial P and I form the real algebraic set, you know, if I join one more coordinate and look at x naught squared equals P inside of R cross Rn, if I project away the x naught, then what I get is P greater than or equal to 0. Okay, so because of this projection axiom, as soon as I have the real algebraic sets, I'm actually forced to have all the semi-algebraic sets. Okay, so that's the next guess, and this actually is our first example. So let R-alg be the collection of real semi-algebraic subsets of Rn. In other words, we let R-alg n be the Boolean algebra of subsets of Rn generated by real semi-algebraic sets. Okay, so just everything that's a finite, you know, obtained by taking finite unions, intersections, and complements of sets of the form P bigger than or equal to 0. And Tarski-Seidenberg says that this is a structure. Okay, so if you look at the axioms, you know, obviously we have all real algebraic sets, and obviously, you know, in each fixed Rn, it's closed under intersection, union, and complement. So the only thing to check is the projection axiom, which is always the hard one. And Tarski-Seidenberg tells you that if you take a semi-algebraic set and project it, you can always write it as, you know, it's contained in the Boolean algebra generated by real semi-algebraic sets. In other words, you can replace sort of in that projection, you can just write it purely in terms of inequalities between polynomials. Okay, so that exactly says that the projection of any element of this Boolean algebra generated by real semi-algebraic sets is again a real semi-algebraic set. Okay, so yeah.
Is that some, sorry, there's someone in my house, so I'm wearing a
No, it's okay.
Is that some kind of quantifier elimination thing? Is it? Or...
I'm glad you asked that question, because that brings me to the next page, which is the connection to first order logic. And this is why model theorists care about this definition. The point is that Tarski-Seidenberg is usually phrased as quantifier elimination for the real ordered field. Because if you think about it, when you take a projection, that's the same as having a, you know, writing down a set in terms of inequalities and sort of polynomial relations that also allows for existential quantifiers, right? Because you're saying there exists an X such that blah, blah, blah. That means it's in the image of the projection. And Tarski-Seidenberg says that if you write down a set which is defined using quantifiers, that I can, in other words, the projection of a real semi-algebraic set, I can get rid of the quantifiers and just write it purely in terms of inequalities between polynomials, i.e. it's in the Boolean algebra generated by semi-algebraic things, okay? So again, the connection with first order logic is the rules I've written down exactly say that the axioms we want definable sets to satisfy, we want them to be closed under first order operations in the real ordered field. In other words, first order operations involving, inequalities and polynomials. Okay, so just going through the axioms, intersection corresponds to and, union corresponds to or, not is complement, and projection is quantifiers. Okay. So let me make one other remark here. I'll be phrasing this always with the real field, but on the model theory side of things, you want to do this for any real ordered field, and the axioms make perfect sense for any real ordered field. And these actually play an important role in the model theory and also in the geometry, because they these bigger real valued fields sort of play the same role as sort of generic points of schemes in a very precise sense. But like I said, I don't want to be talking too much about that. Okay, so just to give us a little practice, it's often useful to think about this first order logic formulation, because it's sort of, a language we're already very familiar with, rather than, appealing to these axioms. So let's prove a very easy, or part of a very easy proposition, which maybe sort of at first sight is surprising. It says that despite the fact that within definable world, within a structure, I'm only ever allowed to take finite unions and intersections. Nonetheless, the Euclidean topology is perfectly definable. Okay, precisely what I mean by that is, given a structure S, taking closures, interiors, and boundaries of a definable set are automatically definable. Okay, so here's the proof. Let's just do it for closures. So take a definable set in Rn, and the proof consists of just writing down a first order formula defining the closure. So here's such a formula. What is the closure? The closure is the set of all points in Rn such that there exists a point y in U which is very close to it. Okay, in other words, there exists a y such that for any epsilon, the distance between this point and y is small. Sorry, I reversed the quantifiers. For any epsilon, you can find a y that's in the set such that the distance is small. Okay, so that's a first order formula, and you can see very explicitly from this formula where the projection is. The projection is coming from the Rn cross R, where I just adjoin x, y, and epsilon, and I just look at the x, y's, and epsilons that satisfy this, and I take a projection. Okay, does that make sense?
So it's not, is it really, is the so I see I understand that the existential quantifier is a projection. So is the for all, is that a projection, or is that like an intersection?
Yeah, I mean, if you take like not, it takes for all to there exists, right? So yeah, you can get for all by sort of taking complements. And then, gotcha. Yeah, other questions? I see, is there, something's happening in chat, but is that for me or is that for someone else? Okay, I'm going to ignore that. Okay, so now we get to O-minimality. I mean, it's like I said, it's very simple. And so before I give you the definition, so I've given you this notion of structure. Remember, we ultimately were interested in, using structure as a language to talk about tameness. I haven't specified any tameness properties. I mean, my structure could just consist of all subsets of Rn, and then of course they would be closed under the axioms, but then I haven't sort of imposed any kind of tameness hypothesis. So O-minimality is a tameness hypothesis. And what it says is that a structure S is O-minimal if the definable subsets of the real line are exactly the semi-algebraic ones. So in other words, a structure is O-minimal if, as far as the real line is concerned, it exactly agrees with R-alg. Or again, said differently, a structure S is O-minimal if the definable subsets of the real line are precisely the finite unions of intervals. Okay? Now that seems like maybe a weak axiom. So the crucial point is that because of this projection axiom, it means something very strong about the definable subsets of Rn, right? You could do something super complicated in Rn, and what this definition is saying is, you know, if I take any of the projections that are allowed within the structure, or, you know, composing with some definable function and then taking a projection, I always have to end up with a finite union of intervals. Okay, so the first example is R-alg is O-minimal, obviously. There's nothing to be said there. Let's give a, oh, I should have said non-example here, but let's take the structure R sine to be the structure generated by the graph of the sine function. Okay, so what I mean by that is take the sets you're forced to have, namely the real semi-algebraic ones, and take this new set that I'm adding, the graph of sine, and then just allow all sort of sets obtained by first order formulas out of these two kinds of things. So that gives you a structure. And it's not O-minimal, sort of by construction, because the graph of sine is not O-minimal, because if it were O-minimal, its intersection with the x-axis would be definable, but that's an infinite discrete set. Okay, so that gives me a subset of the real line, which is an infinite union of whatever length 0 intervals. It's not defined, therefore contradicts the O-minimality axiom. Okay, so let me give a more interesting positive example. Let's do the same thing, but with the real exponential function instead of the sine function. Take the structure generated again by all real semi-algebraic sets, and also throw in the graph of the exponential function, and then allow yourself to use all first order formulas involving polynomials in these things and inequalities, and let Rx be the structure you get. And this is in fact O-minimal. So just as sort of a point of interest, again, connecting back to the model theory, you know, being O-minimal is not the same as quantifier elimination. So we saw that R-alg, it was O-minimal because quantifier elimination held. It is not true that in Rx you have quantifier elimination. Okay, so let's give some slightly, or I guess some examples in a slightly different direction. The main point of which is to say that you can really stuff in a lot of functions into a structure without breaking O-minimality. That's sort of where the power comes from. I mean, there's sort of, you know, sets that are definable in an O-minimal structure, on the one hand, will sort of have nice tameness properties. On the other hand, you really can like get quite complicated things. Okay, so as an example, let's look at this structure. This structure is generated by taking graphs of all restricted analytic functions. In other words, take all functions on a ball in Rn, which are analytic on a slightly larger ball. And just, you know, add all of those into your structure and take all things that are, you know, again, first order formula involving those. And it turns out that this is O-minimal. Okay, this is sort of an observation of Van den Dries. The essential input here is really Gabriel's theorem of the complement. Sort of the hard part for this structure is showing that complements are still definable.
And what is Gabrielov's theorem of the complement?
Yeah, so that is the theorem that a subanalytic set has a subanalytic complement. Yeah, and a subanalytic set is really, you know, I mean, how to say, you know, Van den Dries basically observed that literally what Gabrielov was proving was what was needed. A subanalytic set is a projection of a semi-analytic set. A semi-analytic set is what you would think, the Boolean algebra of things, you know, defined by inequalities between restricted analytic functions. Okay, it's not true for, it's not true, you know, a Tarski-Seidenberg doesn't hold here. Projections of semi-analytic sets are not semi-analytic. So an important point here is you might reasonably say, well, sin x is analytic. We just saw that sin x can't be definable in an O-minimal structure. And the point here is that I've only adjoined restricted analytic functions. Okay, so sin x is certainly restricted analytic when I restrict to any bounded interval. But sin x is not restricted analytic on the whole real line. And the issue is that, you know, I can change I can send x to 1 over x, right? That's a definable change of coordinates. And I would have to have, it would have to look restricted analytic around the origin. And of course, sine of 1 over x looks completely insane at the origin, okay? So if you want another way to think of the sets that are definable in this Rn structure is put Rn inside real projective space. And the subsets that are definable in this structure are the ones that are subanalytic in RPN. Okay. Okay, and finally we get to the one that's, I think for every application to geometry to date, although, I guess I don't know every application to geometry. Certainly for sort of the functional transcendence stuff, this is the structure that's used. And this is sort of obtained by putting together this Rn and this Rx. Okay, so notice the graph of R, for the same reason, the graph of the real exponential is not included in this restricted analytic structure because at infinity, it's not analytic, okay? But somehow the way e to the x looks at infinity is not as bad as the way sine x looks at infinity. And we can throw in the real exponential to this Rn structure, and it's still O-minimal. This is the result of Van den Dries and Miller. Okay, any questions about that?
Can you say what about the exponential function makes this work?
No,
okay.
Not really, but I can give you kind of a cheating answer, which is the following is true. So in general, there aren't many operations, like if you abstractly are given an O-minimal structure, there aren't many things you can do to make it bigger and still have it be O-minimal. There's precisely one such operation that I know, which is you're allowed to essentially adjoin solutions to first order differential equations. And from that perspective, you get e to the x. Yeah.
But second order, I guess, is not good enough.
Second order is bad. Only first order equations. Yeah. Okay. Now, I forget what this slide is about, so let's see. Oh yeah, great. So this is going to start to explain why this R and X is really essential for the applications. Okay. And we're going to look at the complex exponential map. E to the 2 pi I z from C to C star, where we think of C star as the quotient by real translation. And C, I can think of R squared canonically as a sort of can be identified with R squared by taking real and imaginary parts. And C squared and C star similarly, I can think of as the complement of the origin in R squared. So I can talk about definable subsets of C and C star. And so obviously this map is not definable in any O-minimal structure because it has infinite discrete fibers. Okay, so it's not a definable function. However, the next best thing is true, which is that it has a definable fundamental set. Okay, this is very easy to observe. The usual fundamental set for e to the 2 pi I z is just take a vertical strip of length 1. And my claim is, so I should have labeled this F, but so this strip is going to be F. That's my definable fundamental set. And the point is that if I write out e to the 2 pi I z in terms of its real coordinates, it looks like exponentials and cosines and sines. Okay, now exponentials are definable as long as I'm in a structure that contains the real exponential. Cosine and sine are bad on the full real axis, but since I've restricted the real part to be bounded, cosine and sine are restricted analytic, so they're in Rn. So taken together, this complex exponential restricted to the bounded vertical strip will be definable in Rnexp. Okay, so this should immediately convince you that, I have to at least be in Rnexp, even to talk about something as simple as e to the 2 pi I z. And for the applications to, sort of the functional transcendence in the flat case and for Money-Mumford, et cetera, this is the crucial fact that the exponential here has can be restricted to a definable fundamental set such that it's defined, such that this projection map is definable. And so there's something special going on here, because this seems maybe like a baby example, but it's actually an example that generalizes pretty robustly in algebraic geometry. Okay, so let's give essentially the same example, but it'll maybe appear more interesting. And that is, let's look at the full level 2 modular group, namely matrices in SL2Z that are congruent to 1 mod 2. And let's look at the quotient map from the upper half plane to the level 2 modular curve. Okay. Now, I only do, I mean, there's nothing special about 2. I just do that so there's no stackiness. Now, once again, this is not, you know, the Y2 is an algebraic curve. You know, it's an affine algebraic curve, in fact. So it's a closed complex algebraic subset of some c to the n. And in particular, it has a natural definable structure. The upper half plane is obviously semi-algebraic. But this map is not definable because it has infinite fibers. But we see the same phenomenon is true. Namely, there is a definable fundamental set such that the projection map is definable. Okay, and we can see that explicitly. So this is what, if this is the usual fundamental domain for, yeah.
Y of 2 doesn't get rid of the stackiness.
Sorry?
Y of 2 doesn't get rid of the stackiness, just to complain.
Oh, is that true? Okay, whoops, yeah. I should have thrown in 3.
Yeah, sorry.
Y of 2 doesn't. Yeah.
It is a gerb over an honest curve. Right?
Yeah. It's just the generic stacking. Okay, well, whatever. I care about that less. Yeah. So here's the usual fundamental domain for the full SL2Z action. So this sort of bold outlined thing is a fundamental domain for a fundamental set for gamma 2. This is obviously semi-algebraic, right? I mean, these are like circles and lines and stuff. So this is a semi-algebraic subset of the upper half plane. And then so call this F. And the important point, I already said this, so Y2 is an algebraic curve, so it has a definable structure. And the point is that this projection map, when restricted to F, is Rnx definable. Okay? And just to very vaguely tell you why this is, I mean, we have Rn in there, right? We have all restricted analytic functions. So the fact that this is sort of definable everywhere except the cusps is kind of clear, right? I mean, you know, the algebraic, I mean, what is this saying? It's saying I can define the coordinate transformation going from the algebraic coordinate to the upper half plane coordinate is restricted analytic everywhere except the cusp. That's totally true.
So when you say it's definable in a region, do you mean that there exists like if you restrict it to that region, you get a definable function?
Yeah, so precisely what I mean in order for this to make sense is, yeah, you would want to sort of take a finite atlas by definable sets and sort of check that those maps are definable, right? And so what I'm saying is you can take an atlas for Y of 2 that consists of sort of algebraic open sets, and ones upstairs that consist of semi-algebraic sets in the upper half plane. And as long as I'm not going to the cusp, then everything's totally fine. The issue is the cusp, and now the point, and you can, if you think about it, you'll see that, you know, I'm not even lying. I mean, this is basically a proof. At the cusp, the algebraic coordinate looks like e to the 2 pi I z. Okay? So it basically reduces to our previous example. So something important about the cuspidal geometry of uniformizations of algebraic curves. And in fact, this is the machine sort of underlying also the same picture for the seemingly more complicated situation of like the uniformization of the moduli space of principally polarized abelian varieties. Okay, great. So that gives you an idea of sort of how definability will arise in geometry. Let me give you an idea for, so I mentioned that sort of this O-minimality axiom is going to give us some nice tameness properties. As far as I know, there's one expression of that tameness that's like universally useful. So if you understand this one theorem, you basically understand all the structural properties of definable sets. Okay, and this is definable cell decomposition. Okay, so this is going to be a little bit of time, but I think it's probably worth going through because again, it will give you a very clear picture of the sort of nice properties that definable sets, sets that are definable in an O-minimal structure satisfy. Okay, so a definable cell decomposition of Rn is just a partition into pairwise disjoint definable subsets of a particular type. Okay, so here, throughout this discussion, I'm just fixing some structure S. And whenever I say definable, I mean definable with respect to that structure. Okay, so these cells have an inductive definition. So in R0, there's exactly one definable cell decomposition, and it just consists of one cell, which is everything. It's just the point. Okay, the interesting part is the following. So assuming I have what is a cell decomposition of Rn? Well, first we have to choose a coordinate projection. Okay, so we write Rn as Rn minus 1 cross R. We choose a definable cell decomposition on Rn minus 1. And from that, I'm going to build a partition of Rn using two types of operations. Okay, so this is maybe a little complicated, but I'll give you some pictures that'll make it more clear. For every cell E of Rn to the minus 1, I'm going to give myself some finite collection of functions which are ordered, meaning sort of you have the same ordering above every point. And the two kinds of cells above that cell in Rn minus 1, above E, that I'm going to allow are the graphs of these functions and the bands, in other words, the moving intervals between the functions. Okay, so let me just leave this for like 1 minute. You don't, I think the pictures give you a more clear idea of the definition than the actual text, but just to give people a chance to finish reading it. Okay, so let's start with n equals 1. This is very easy. So if I go back to this definition for n equals 1, what does this mean? I need to specify a cell decomposition of R0. Okay, there's exactly 1. I need to give myself finitely many functions over the unique cell of R0. In other words, a function over a point is just some value in the real line. And then I allow two kinds of cells, the graphs, which are just those points, and the bands, which in this case are just the intervals. Okay, so a cell decomposition of the real line just consists of giving finitely many points in the real line, and the cells are those points together with the intervals between them. Okay, so it looks like this. This is what a cell decomposition of the real line looks like. Sort of obviously, it's the only thing it could look like. Okay, slightly more interestingly, let's look at the R squared. And once you have it for R squared, you'll have it for Rn. So again, inductively, we need to choose a coordinate projection. We need to choose a cell decomposition of the real line. So let's take this one. And then this is a picture of what a cell decomposition of R squared looks like. Okay, so here you can see that these guys all project to one of the cells on the real line that I had before. Right, that consisted of like points and then the intervals between them. And then over each of those cells, I have the graphs of these functions. So these sort of solid black things are an example of graphs of functions. And these like shaded regions are bands. So there's some sort of moving intervals between those functions. Okay? Again, I'll give you a minute to stare at this picture.
Do the marked points mean anything, or are they just?
These are also cells. So these are, notice, above every 0 cell of the real line, you get a definable cell decomposition of the preimage of that point, which is just a vertical line. So on each of these vertical lines, you get a cell decomposition of that real line, consisting of, these points are the graphs of functions over this point, and this interval is the band.
Got it.
So I do this sort of band and interval construction for every cell on the Rn minus 1. Yeah.
So for R3, you'd kind of extrude this picture out of the screen, and then every face and so on, you'd also break up this way.
That's right. So if you imagine like sort of putting this on top of the table, then over each one of these things, you'd have some ordered sequence of definable functions. And you include sort of the space between them and the graphs of those functions themselves. And you do that for every one of these cells. Okay, so here's the theorem. The theorem is that if you give me any sort of finite collection of definable subsets of Rn, then there exists a definable cell decomposition of Rn such that each uj is a union of those cells. Maybe I should have said even better, like, I mean, implicit in the definition is a choice of ordering of the coordinates. So I can also, given the finite collection uj, I can first choose an ordering of the coordinates, and then there will be a cell decomposition sort of using that ordering such that each uj is a union of cells. Okay, so let me observe one thing super quickly. This already says something, I mean, it says something kind of interesting. It says that any definable subset has sort of a well-defined dimension, namely that you take a cell decomposition, you take a cell decomposition of Rn such that, U is one of the cells, is a union of cells, and you just take the maximum of the dimensions of the cells, because obviously each cell has a maximum dimension.
Is it obvious that that's independent of the decomposition?
It's not 100% obvious, but it's pretty easy to prove for yourself. But again, this is not obvious. So for instance, let me give you a super quick application. Again, you can convince yourself of, but is not at all obvious. Like if I had just said it to you, if you take any sort of set that's definable in Rnexp, anything that's defined by some crazy, first order formula involving exponentials and restricted analytic functions and stuff. You take any such thing, you take the closure, and then you remove the interior. So in other words, you look at the boundary of that set, that has smaller dimension. Okay, so that already tells you something about sort of the sparsity of the boundary of a set, which is not true if you take sort of random subs. You can easily make whatever. It means that you can't have like space filling curves and like crazy stuff like that, right? Things that have are much tamer. Okay, so let me give you sort of two essentially immediate consequences of cell decomposition, which are super useful in working with this stuff. And the sort of common theme here is that if you have definable families of stuff, then you sort of get uniform boundedness for free. Like if sort of fibers are finite, then they're uniformly finite for free. So here's an example of that. So take a definable map from U to V. And for each n, look at the subset of V such that the fiber dimension is n. Okay, then that's a definable subset. Okay, then it's sort of immediate by cell decomposition. Well, okay, in this case, the fact that there's uniform bound of the dimension is not so interesting. But let me quickly give the proof. The proof is basically take the graph of this function, but now order the coordinates backwards. And the point of doing that is that, because of the inductive nature of these cells, they always project onto the sort of previous cell decomposition with constant dimension. Okay, so if I sort of order the coordinates backwards, then, I'm constructing the fibers, and what it means is that the fiber dimension is constant along whole cells. Okay, and therefore these sets are just unions of cells. Okay, so if we go back to this picture, you should imagine sort of the graph of a function, but then reflected through y equals x. So it's sort of graphed as x equals f of y. And taking a fiber means like taking, vertical intersections with vertical lines. And you can just see from this picture that the intersection with any vertical line is sort of constant dimension over each cell. Okay. Okay, so let me give you something that's more useful, but that's the same proof. And then this is more what I was talking about in terms of uniform boundedness. If you have a definable map, U to V, with finite fibers, then I can look at the sets where the fiber size is a particular thing, n. So first of all, that's definable. And second, there's a uniform bound on the size of the fibers. Okay. So again, this is sort of something that's much more reminiscent of algebraic geometry than it is of like, real analytic geometry or something. You can easily have function, fibers that go crazy without any sort of tameness hypothesis. And this is saying sort of we're much closer to kind of the tameness properties that exist in algebraic geometry. And this is an actual use. I mean, this comes up over and over again, this uniform boundedness principle.
Can you say why the size of the fibers is uniformly bounded?
I guess it's a corollary of the proof, but the point is I mean, it's the same proof as before. You take the graph of the function and you you find a cell decomposition with respect to the sort of reverse ordering of the coordinates. And then the point is that, once again, over cells, you have the same fiber size. So then it's clear there's uniform bound because there's finitely many cells.
Well, oh, sorry. Why are there finitely many cells? Maybe that's what I don't understand.
That's part of the theorem. That's a cell decomposition is a finite partition.
But I'm confused. So when we took a cell decomposition of Rn, that wasn't finite, right? Was it?
Yes, it was.
Oh, okay. So that was part of the statement. I see.
Yeah. Sorry. Yes. I hope I said it. Well, yes, I certainly said it here. Into a finitely many. Yeah. No. There's definitely. I mean, maybe it wasn't clear from this picture, but right. These sort of like corners are infinite.
Yeah. Now I got it now. Right.
Yeah. No. It's essential that it's fine. Okay. So, so like I said, I mean, if you understand cell decomposition, you basically understand everything about, definable geometry, O-minimal geometry that ends up being useful in terms of like what properties what nice tameness properties do O-minimal sets have that arbitrary sets don't have. So I encourage you to sort of ruminate on cell decomposition. But just in the last sort of 10 minutes, let me sort of finish by coming back to this Pila-Wilke theorem and talking more generally a little bit about algebraization within the O-minimal context. Okay, so the important point here is that the tameness we get from being definable in an O-minimal structure implies algebricity in two distinct ways. Okay, the first is arithmetically. The statement is sort of coarsely speaking is that if you have a set that's definable in an O-minimal structure that has many rational points in a certain precise sense, then it's forced to be algebraic. And the second is a more complex.
What does rational point mean in this context?
I literally mean you have a subset in Rn that has lots of Qn points.
Okay.
And then I'll come back. I'll talk more. I'm going to talk more about the Pila-Wilke application than the complex analytic perspective. And then the second algebraization theorem is that if you have a sort of a complex analytic subvariety whose underlying set is definable in an O-minimal structure, then it's forced to be algebraic. Okay, so both in complex analysis, the tameness that definability gives you implies algebricity. And arithmetically, the sort of tameness that definability gives you implies algebricity, if there's some arithmetic. Okay, so let's just briefly, and then I'll do this quickly because I'm sure you're already talking about this, but let me just quickly talk about the kind of height that I want to be talking about. So if I have a rational number, the height is just the max of the numerator and the denominator in lowest terms. And if I have a tuple, something in Qn, then it's just the max of all the heights of the coordinates. Obviously, there's sort of in Qn, there's finitely many points of bounded height. If I take a subset U of Rn, I'm going to define the following notions. So first of all, this is the counting function. It counts how many rational points this set has of height t, or height bounded by t. Okay. Second, I'm gonna define the algebraic part of U to be you take the union of all connected semi-algebraic positive dimensional things that are inside U. Okay, this is kind of a weird notion, and it won't have much meaning unless U is already sort of definable. But this is the definition. Okay, that at least makes sense as a definition. And then the transcendental part is just going to be the complement of the algebraic part in U. Okay, and notice even if U is definable in an O-minimal structure, U-alg, is not going to be. I mean, this is going to be some weird, U-alg is going to be some hugely infinite union of stuff possibly. Okay, so now let's state the counting theorem. So let's let's just recall what Pila-Bombieri said. It said that if you take like a non-algebraic, compact, real analytic curve, and you scale it up, it gives you some control on how many integer points that has. Well, looking at integer points on the scaled up thing is just the same as looking at rational points on the original thing of bigger and bigger height, okay? So the sort of final form of Pila-Wilke that generalizes the Pila-Bombieri statement is that if you have a subset of Rn, which is definable in an O-minimal structure, then there are fewer than polynomially many rational points when counted by height, ordered by height on the transcendental part. Okay, so precisely that means that for any epsilon, the number of rational points of height t on the transcendental part of U is less than t to the epsilon for times some constant. Okay, so the moral here is the transcendental part can't support a lot of rational points. Again, in this sense of sort of the asymptotics with the height. Okay, so I call this an algebraization theorem because the way this is used is if you have a definable set which does have more than polynomially many rational points when ordered by height, that implies that there must be an algebraic part, a semi-algebraic part. Okay, and that's already a pretty strong conclusion. So if we go back to Pila-Bombieri, you can sort of recover that statement. If we had if we have a curve in R2, which is definable in O-minimal structure that is more than polynomially many points, it has to have an algebraic part, but that just forces it to be algebraic. Okay. So notice, let's now that speaking of Pila-Bombieri, we were talking there about compact real analytic curves. Notice that those are exactly definable in Rn. And we start running into trouble when you go to infinity if you just allow anything. So the sort of insight of this theorem is to realize that being definable in an O-minimal structure is the precise sort of tameness property of the asymptotics of the curve to make sure that the theorem still holds. Okay, and we can even sort of give the idea behind the proof. I mean, remember the proof of...
So can I go back to that example I asked about at the very beginning about y equals 2 to the x?
Mm-hmm.
So there, this is, I guess this is saying that so that's definable in Rnx.
Mm-hmm.
Right? This is saying that the y coordinates of rational points have to be growing very, very fast.
That's right, yeah. So if you look at this counting function, you certainly don't get polynomially many points when ordered by height on 2 to the x. Yep.
Thanks.
And so I mean remember in the proof before, there were sort of two components to the proof. The first component was that if you have some bound on the derivatives, then your function can't be too wiggly in a controlled set, in a sense that's invariant under scaling. So with higher and higher degree d curves, you can sweep out all the integral points more and more efficiently. And then the second important point was that in this compact family of degree d curves, there's a maximum number of intersections you can have. And now it's sort of clear that definability, that in that latter statement, if I replace compactness with definability, I still get the uniform boundedness that I had before by this sort of uniform boundedness result that I mentioned. And likewise, in the first part, I'm also talking about sort of, well, it's a little more complicated there. But anyway, at least in the second part, it's sort of clear how to replace compactness with I mean, that's sort of the moral here is that you can replace compactness with definability because definability also gives you uniform boundedness of stuff. Okay, so I have a couple minutes left. So let me talk about this. So this was the arithmetic algebraization theorem. Let me talk a little bit about the complex analytic one, because in some sense that's even easier to see how definability is working for you. So the theorem is that if Z is a closed complex analytic subvariety of Cn, whose underlying set is definable in an O-minimal structure, then it's algebraic. Okay, so this is the theorem of Peterson-Starchenko. It's called Definable Chow, because if you remember, the sort of analytic Chow says if you drop the definability, but additionally require that you're in an ambient compact algebraic variety. Okay, so definable normal Chow says if you have a closed analytic subvariety of Pn, then it's algebraic. So this is saying, okay, well, let's drop the compactness, but let's add this tameness property. Then the conclusion still holds. Okay. And as sort of a baby case of the theorem, and this really is the sort of crucial insight behind it, and then you sort of use the fact that definability works well with respect to sort of inductive arguments involving projections and stuff. The sort of baby step is to realize that a definable an entire function from C to C, which is definable in an O-minimal structure, is algebraic. And that's just from first year complex analysis. The point, if you have a definable function from C to C, if it had an essential singularity at infinity, it would have infinite fibers. And that's not allowed if it's definable in an O-minimal structure. So it has to be algebraic. Okay, well, that's all I wanted to say.
Yeah, let's thank Ben. That was really great. Ben, do you have a few minutes for questions?
Sure, yeah.
Okay. Does anyone have any questions for Ben? So I have two questions.
Yeah.
So my first one is maybe dumb. So e to the z is not definable, I guess, by the last theorem. Is the reason, I guess, the imaginary part is sine?
That's right, yeah.
Cool.
And notice that, I mean, you know, it's always going to be the complex exponential will be the easiest counterexample, but that's also a counterexample to this sort of non-compact Chow theorem, right? If you take the graph of e to the z in in C cross C star, that's a closed, you know, complex analytic subvariety, which is not algebraic.
All right. And my other question was, so you defined everything kind of relative to an ambient Rn, right? So you defined ambient subsets of Rn. So I'm wondering, is there a more coordinate-free notion of O-minimal geometry? Like, can I have an O-minimal space, not like which is locally modeled after?
Absolutely, yeah. And this is something that, so, you know, you can sort of very easily make topological categories. Like you can first talk about definable topological spaces, which just have sort of a finite atlas by definable sets with sort of continuous definable transition functions. Then you can talk about sort of definable topological manifolds. And that's something that's certainly been looked at. Sort of, we developed the notion of sort of definable complex analytic varieties, which is just sort of the same thing, except now you also carry around a sheaf of sort of definable holomorphic functions. But yeah, you can certainly do geometry that's sort of locally modeled on definable sets. The only thing you have to be a little careful of is sort of definability. Necessarily, it's a little interesting. Sort of definability is sort of halfway between, you know, local and global, right?
I guess the projections are kind of global.
Sorry?
The projections are kind of global.
Well, it's not so much that. I was going to say, like, you know, if you want to develop the sheaf theory, you can only use sort of finite covers at every step. Because, I mean, for instance, you know, Rn contains all restricted analytic functions. So if you allow arbitrary covers, then there's like no difference between like a holomorphic function and a definable holomorphic function, because any holomorphic function is locally definable. So so the sort of, yeah, the tameness that definability offers is sort of a combination of its it's globally topologically simple and locally has some sort of simple stuff. Yeah.
Are there other questions for Ben?
Maybe kind of a basic one, but in this, when you go to define a cell decomposition, it sort of looks like you can recover like a cell decomposition in the sense of algebraic topology from this. You know if that's the case?
Yeah, I mean, indeed. I mean, each of these cells, I mean, it's not hard to convince yourself that each cell is sort of definably homeomorphic to Rn of, you know, whatever Rk for whatever the dimension of the cell is. And I mean, it depends what you're at. I mean, the answer to your question is going to be yes in every possible way that you mean it. So depending on sort of what exactly you want your cell decomposition, what properties you want it to satisfy, you can find a finite decomposition that will be satisfied within definable, if you have a definable topological space. So for instance, something that's not true right off the bat for a cell decomposition of Rn the way I've defined it, that you often want in applications is it's not true that, for instance, like the boundaries of cells are like unions of cells or like things like that. Okay, but you can easily show that, like, with this, I just chose, this is the easiest to state. You can easily show that you can like refine this so that that's true and things like that. Refine it in a finite way. So yeah, for sure. Mm-hmm.
Cool, thank you.
Sure.
Any other questions for Ben? Well, if not, Ben, thank you so much. That was really fantastic, and I'm excited for some what's coming. All right,
cool. Yeah, my pleasure.
Yeah.
Let me know if if there's something wrong with the handout version of the slides I sent you that I can easily fix, and then I'll send you the correct version.
I looked through it and didn't see anything, so yeah, I think it's great. But
okay, cool.
So it's up on the website, assuming that's okay. Oh, maybe let me stop recording.